Okay, this is on page 252, section 5.4, and the title of it is Equilateral and Isosceles Triangle. So we're going to add to your list of things that you can use in triangles to get certain things equal to each other. And it has to do with whether the triangles are isosceles or equilateral. You can make certain conclusions if you know that. First thing is called, well, before the first thing, we got to learn to use some vocabulary on isosceles triangles. We have an isosceles triangle like the typical one we think of, where two of the sides are the same length and the other one is not. That's typically what we think of isosceles. There are certain parts of this triangle, if you know this is what you've got, that they have certain names, and in order to be able to talk about them, you got to know what they are. These two guys that are equal, they are called legs. They do not always extend from the top to the bottom like your legs. You could have an isosceles triangle drawn like this over on its side. And if it is these two that are equal, then these are the legs. We're not going to distinguish between them because they're the same length. So you got your two legs. They're the ones that are the same length. The one that is not equal to those two, there's only one other side. We call it the base. And base does not mean bottom. As in the case over here, the base is actually extending as a vertical line. It just happens to be the third side that we call the base. Okay? Does not mean bottom. There are two angles that are formed with this base. This one that comes across the base like this and then heads up that leg, and the other one that comes this way and heads up that leg. There are two base angles down here, and that's what we call them, base angles. This is also a base angle. And there's only one other part, and that's the angle at the top. By the way, these are the base angles here. Depends on where the base is. It does not, and we quite often see isosceles triangles drawn like this. So the base is actually at the top, and these are the base angles. Got an idea what a base angle is? Okay. The last thing that has to be named is that remaining angle. And I don't know who did this, but I think they got tired of naming things at this point because it's a really dumb name. It's called the vertex angle. They're all vertexes. Any corner is a vertex. But this is called a vertex angle. And those two words together only belong to isosceles triangles, and it only belongs to the angle that is formed by the two equal sides, which are legs. I suppose we should call that a leg angle, but we don't. We call it the vertex angle, so we're used to it. So these are the 6 parts of an isosceles triangle, okay? That being said, we're going to go to what's called the Isosceles Triangle Theorem. And if you're going to use it in a proof, that's your abbreviation. ISOS, triangle symbol, theorem, THN. So if you're going to use the isosceles triangle theorem as a reason in a proof for saying something, that's what you're going to write on the right side of your proof where the reasons go. And it says this, and if you're not paying attention very well right now, or you're not 100% with me, you better get 100% with me because you will mess this up if you don't pay attention. This is what the isosceles triangle theorem says. If two sides of a triangle are equal, then, the conditional statement, then the angles opposite those sides are equal. Now we need to talk about what opposite means. In any old plain old generic triangle event, not of any particular type, forget this for just a minute, just plain old triangle, whatever it happens to look like, this side right here is opposite of this angle. It's the third side. It's the side that's not forming the angle that it's opposite to. So if you're looking at this angle, this side's opposite of it. I put a C up here and I say angle A is opposite to side CB. You see that? It's the side that's not formed by the sides of A. Okay, so what this tells me is if I've got a triangle with two sides equal, like this, not of any particular orientation. I know the two sides are equal, so that's the if part. If two sides of a triangle, there's my triangle, are equal, I got them marked, then the angles opposite those sides. Okay, here's one of the sides. What's the angle? What angle's up? I'm going to put some letters on here so you can refer to it with me. What is opposite of this side? A. Just A. Angle A is opposite this side. What's opposite this side? Angle C. The angles opposite those sides are equal. They always happen to be the base angles, right? Now here's the part you got to listen to. If in a proof they tell you that you've got a triangle that's isosceles, in the beginning it says triangle ABC is isosceles, you cannot immediately say that the base angles are equal. And the reason you can't is because this theorem never mentions the word isosceles anywhere. It only talks about sides and angles. So, what I'm saying to you is, and this is the part that's going to hang you if you're not paying attention right now. If I give you a diagram like this for a proof, and I tell you in the given, I say in the given, triangle ABC is isosceles. This is what you cannot do. This is what you cannot do. You cannot in this step say angle A equals angle C. You cannot say that. Because this says if you have two sides that are equal, do you see where we've ever said that the two sides are equal? There's no place ever in this proof yet that says we have two equal sides. So you cannot go to the angles until you have said the sides. So this is the proper way to do it. You look at that and it's very clear that AC is not as long as those others. So we say, the ones that are more clear, we say AB equals BC. Now, why would that be true? Yeah, because you know what an isosceles triangle is. You know its definition. If you're told that triangle is isosceles, you know by now that means it's got two equal sides, which you just stated. So this is the definition of isosceles triangle. Now, and only now, can you say angle A equals angle C. If you want to say, and that would be the isosceles triangle theorem. Because we have two equal sides, so we have the angles which are opposite those sides. And if we mark them, we're well on our way to getting some sort of congruence, although I have only got one triangle there. I'm just saying, you can't say that the angles are equal until you have said the sides are equal. And you can't get the sides equal unless you know you're dealing with an isosceles. Now, just for the sake of variety, let's say that this thing started out like this, same picture, and in the given it said AB equals BC. Now can you say that angle A equals angle C?
No, what it was.
No, you can. All you need is two equal sides. Two sides are equal. If they tell you that right at the beginning, and you can see that they're sides, you can immediately say that the angles are equal. But sides make equal angles, not isosceles triangles. Equal sides make equal angles. And if they give you equal sides in the given, then yes, you can say the angles are equal next. But if they give you that the triangle is isosceles, then you have to get the sides from that definition and then the angles. You can't go from here to here because there's no mention of the word isosceles in the theorem. You have to be careful. Do you understand what I'm telling you? Be careful with that theorem. It's a nice, handy theorem, but it takes three parts. You can't just go from isosceles to angles. You can go from isosceles to sides and then from sides to angles. Okay, I'm going to erase this. And there is what's called the converse isosceles triangle theorem. And it goes backwards. This says, if equal sides, then equal angles. What do you suppose this one, next one says? If equal angles. If two angles of a triangle are equal, then the sides opposite those angles are equal. Now, where might you use that? Well, let's say that you've got that same diagram. We'll even call it ABC again. And this time, you're trying to prove triangle ABC is isosceles. That's what your goal is to prove it's isosceles. Now remember, definitions are biconditional. Remember? The definition of isosceles says, if a triangle has two equal sides, then it's isosceles. It also says, if a triangle is isosceles, then it has two equal sides. Did I just say that? If a triangle is isosceles, it has two equal sides. But it also says if you have a triangle with two equal sides, then it is isosceles. Follow that at all? So if I'm trying to prove that ABC is isosceles, I have to show that AB equals BC. You have to show that. So if someone proof, I don't know, say step number 4 or something, you have established that angle A equals angle C. You cannot say that the triangle is isosceles now. Got it marked here. You look at the angle, but it is. It is isosceles. No. All you have is two equal angles. What you have to do in step number 5 is say AB equals BC. What would be the reason for that? If you knew that angle A equals angle C, how do you know AB equals BC? This. You have two equal angles, then the sides opposite them are equal. Those are the sides opposite. Converse, isosceles triangle theorem. Once you've established that those two sides are equal, then you can say the triangle is isosceles. And that's by definition, backwards. It's still the definition. Get two equal sides, you got an isosceles triangle. But you can't go from angles to isosceles for the same reason. There's no mention of the word isosceles here. You got to have two equal sides to make a triangle isosceles. But you can get from the angles to those sides using the converse, isosceles triangle theorem. Okay, so let's see it in action here. Actually, I want to tell you about the corollaries first. The corollaries, remember what a corollary is? It's another truth that follows right on the heels of something we just discussed. There's a corollary to this one right here that says, if it's not an isosceles triangle but an equilateral, got an equilateral triangle, all the sides are equal. So which ones are the legs? And which one's the base? Well, if these two are the legs, then this is the base. If these two are the legs, then this is the base. And if these two are the legs, then this is the base. So they can all serve as the base if the other two are the legs. You go, how do you tell? And the answer is you don't. This is one of those things I was telling you that isosceles triangle has at least two equal sides. This is still an isosceles triangle with all the properties. So if it's these two that are equal and this is the base, I know that this angle equals this one, right? If it's these two that are the legs and this is the base, then I know that this angle and this angle are equal. Which means they're all equal. We knew that. In an equilateral triangle, if you know it's equilateral, you know it's also equiangular. Furthermore, those angles are all 60 degrees. Y'all with me there? And if you have a triangle where you know all of the angles are the same size, you know that, you can immediately say that the sides are the same from this. So all I'm saying is, if it's equilateral, it's equiangular. If it's equiangular, it's equilateral. If you know equal angles, you know equal sides. If you know equal sides, you know equal angles. And all the angles are 60. That's a corollary. And that is found on page, in the middle of page 283. So, here we go. We're going to do a couple of proofs here using this theorem. By the way, you want me to prove that theorem, kid? We can prove it if you want. No? You don't want to see that proof? If you do, this is the bottom of page 252. You can see it actually proves that those two theorems are correct. Okay. Actually, I don't think that, I'm not sure that there aren't any proofs, so you can use it if, I think there is. Let's see. There may not be any proofs on this section. So we're going to use these facts to write some equations and find x and stuff like that in different situations. So look at page 254, example 3 at the bottom. We're not going to do any instructions, and that's what they're showing you at the top. So if you look on page 253, or 254, excuse me, at the bottom there, it says example 3. I think I'll put this on the board so that we can fill some things in. This one's kind of weird. What we've got is a triangle like this. We've got that coming down that way, and these are all equal. No, the angles are all equal, but it means the sides are, so we'll get that. This angle equals this one, and this angle equals this one. Shh. We have an x plus 1, a y, and a 4. And here's our goal. Here's what we're supposed to do with this. Find the value of x and y in the diagram. I'm going to grab a different color here so we can see all the stuff that's black was given. We have to find the value of x and y. I think y is pretty easy. Do you?
Yeah, it's 4.
It's 4. Has to be, because if this is equiangular, then this triangle here is equilateral. So we know that y equals 4. I'll put it over here. And I'll even put it on here. Now we got to go find x.
Well, that one is like if y is 4 and the other angle is 4, and the last one needs to be 4. And then
This one here?
No, the
This one over here?
No, the other one.
This one here?
Yeah.
This one's got to be 4, as you're saying? Do you agree with her?
Mhm.
So they didn't ask us to find that, but we're going to need it, right? So this is 4 right here. Because it's an equiangular, it's equilateral. So you're right. That piece right there is 4. What else?
So if those two angles are equal, then 4 has
The two with the double bands?
Yeah.
So we got the double bands right here on this one. So now we're focused on this triangle, which is, well, we haven't said it's isosceles, but it's got 2 equal base angles, which means we can get the sides equal. Oh, the sides equal. Oh, see what she's talking about? If this is 4, this has to be 4. Because of this triangle being isosceles, these legs have to be the same length. You see it? So we write 4 equals x plus 1, and we get 3 equals x. So you have to go from one triangle to the next, and remember this one's isosceles, this one was equiangular, so these are all equilateral, and since this is isosceles, these legs have to be the same, it causes an equation. So there's some thinking to do there. My advice to you again is that if you get a complex problem like this, that you actually draw the picture and you fill in everything you can possibly figure out, this one in particular, and circle them or write them in a different color or something so that you can go from this triangle and lead into this one because they share that side. Find all the things you can and then answer the questions they ask and you get all set. Okay. Now I want you to take a look at example 4. I think it's the last one. And then we're going to look at the monitoring progress because it's got a good problem on it too. Okay. Example 4. They're trying to make things real for you again. I'm not going to try to make them real. We still have to do them. They give you this stand where this lifeguard sits up there on the beach. And you need to look carefully at the picture. Can you see the diagram that they're talking about? Really hard to see. You see the P, the Q, the R, S, and the T? And the angles 1, 2, 3, and 4, you see them? If I were to draw that picture, something like this, straight down and then over here, got this across here, and they want us to talk about this situation. Right? Is that what we got?
Yes.
We got the angles 1, 2, 3, and 4, and they mean these. Oh, not that. Where's the 3? Is it down here?
Yeah. That was 4.
This is 3?
Yeah.
Okay, so we got those angles and we got some letters here. S, R, Q, P, T. S, R, Q, P, T. All right, now we've got things completely drawn now. It says, in the lifeguard's tower, it says PS equals QR. So we'll mark that. It's kind of like doing a proof. Mark it what we know. See what we can conclude. And QPS equals PQR. QPS. PS equals PQR. Okay. So this whole angle here is equal to this whole angle here, is what they're saying. Now, the question asks, A part, explain how to prove that triangle QPS equals PQR. QPS. So if I pull them apart, we're talking about these two triangles here. It doesn't say to do the proof. It says explain how you would do it. Not very hard. How would you do it?
Wouldn't PQ equal PQ?
That's what you're gonna say? In the shoved together picture, it's one of those reflexive deals. So all you would have to do to prove it, say, if I was gonna prove it, I would say PQ, PQ reflexive, and then get side angle side. So you'd have to write. You okay on that? If you pull them apart, it's a lot easier to see. Then the B part says, explain why PQT is isosceles. PQT. PQT. Ooh, they're talking about this guy up here, and we lost that triangle when we yanked these apart, but we want to see if we can figure out why this triangle has to be isosceles. I'm going to put those down here in my busted out one. And let's see, angle 1 would be here, and angle 2 would be here. Okay. We can only talk about it, the one that's shoved together. That gives us triangle PQT, and we're trying to decide why that one's isosceles. But you can use this pulled out one here, because think about this with me. This is what's coming up in the next section tomorrow. You might as well just start thinking about it. Is it true that angle 1 equals angle 2? Why?
Was it like the two angles?
Well, angle 1 and angle 2, when you shove them together, it's these guys right here. That's the question mark. How do I know that those two have to be equal? And look down here and you can tell. First of all, let me ask you this. Are angle 1 and angle 2 in this broken out piece right here, are angle 1 and angle 2 corresponding parts? Remember, there are 6 parts of a triangle. Ladies, if you're not interested, please take your conversation elsewhere or stop it. You agree that 1 and 2 are corresponding parts of these triangles? They go together, right? Didn't we just say that this triangle equals this one? Doesn't that mean that all of its 6 pieces that go together have to be equal too, because they're equal? It's kind of thinking backwards. Before, in the section that we did before, we said if all 6 parts are equal, then the triangles are equal. Then we cut it down to just 3 apiece in certain patterns, right? But it's still true. I mean, if we think backwards, if all 6 parts are equal, then the triangles are. But if we know that the triangles are, then any of the remaining 6 parts have to be as well. The parts on these 2 triangles that I know for sure are equal are P equals Q. That was given to me. I also knew that QR equals PS. We got this reflexive. So these 2 triangles are equal to each other, which means all their little pieces that haven't been marked yet are equal to each other. Now, let me show you what that looks like. It's going to be a reiteration of your lecture on tomorrow. If I know that these triangles are congruent, I only know 3 of their parts. I know this side equals this one. I know this side equals this one. I know this angle equals this one. But there's 6 parts altogether, which means I know that angle 2 equals angle 1 because they correspond. I also know that 3 equals 4 because they correspond. And if I wanted to, I could say that QS equals PR because they correspond. And so we have this abbreviation, and people always forget what it stands for, and that's what kills you. It says, what we're saying is this. All its discussion says that corresponding parts, which we write like that, corresponding parts of congruent triangles are congruent. It's a shortcut way of writing, but people forget how to use it. They haven't any idea how to use it. This is what we just said. Corresponding parts. That's what 2 and 1 are. Those are corresponding parts. Now we have a prepositional phrase. Of congruent triangles. That's what these guys are. These are corresponding parts of congruent triangles. We know the triangles are congruent, right? Are congruent. What are? The subject of the sentence. That's what. And the subject of the sentence are the corresponding parts. So these corresponding parts, 1 and 2, of congruent triangles, they have to be corresponding parts of congruent triangles. If they're just corresponding parts of 2 triangles, you haven't proved they're congruent, then this doesn't hold. You have to prove this first. And you've been practicing that for 3 sections. You have to prove that the triangles are congruent. Then, if you want to carry it beyond that, then you can say any of the remaining parts that aren't marked are equal for this reason, CPCTC. but you gotta have this. It surprises me, it amazes me when people turn in these, and this is one of the first reasons they use. This is one of the last reasons you'll use. Usually the last, because you have to get the triangles congruent before any of the corresponding parts can be. Because you spend most of the proof getting the triangles to be congruent. And then if you go one more step, you can say any of the corresponding parts you want can be. So the answer to this one is in the B part. It says, explain why PQT must be isosceles. And the reason would be because angle 1 and angle 2 are equal, CPCTC. Therefore, PT equals QT, or converse isosceles triangle theorem. So this is isosceles by definition. It's quite a process. You get that, you got that these were congruent in A, so you know the parts are. So you get that. You say 1 and 2 have to be equal. Here they are. Those two are equal. That means PT equals TQ because of this. That means this is isosceles by definition. So you have to go through all that bit of reasoning to show it. But we're going to learn this and practice and practice and practice with this on tomorrow. Okay. Take a look at the monitoring progress with me for just a minute. On the bottom of page 255. Okay, so here it says, find the values of X and Y in the diagram. And X and Y are both angles. So I'm going to erase this over here now and draw that picture. Use a little bit more of the board. Okay, this picture is kind of hard to draw, so give me a second. We got a right angle and an obtuse triangle. A right angle coming down like this, and then this is obtuse coming up like that. Did I get that right?
Yeah.
Okay. And in the markings that we see on the diagram, we have that right angle and a whole bunch of equalses. We have this is a right angle. We know that this side equals this one, and we know that all of these have the same mark. Is that correct? I got to mark all up, right? Okay, and then I've got an X here. Is that right? So this one's Y, and this one's X. Is that right? Okay, let's look at the reasoning behind this. If all of those marks are true, then finding X is easy, or it should be. What is X? 60, because it's one of the angles in this equilateral triangle that we know is equilateral because of the marks. So I'm going to take a different color, and you can too, or you can just circle. A lot of times if you're just going to write with pencil, then you put a 60 here because that's what X is. But we also know because of it that these are both 60. So the red ones are things I'm coming up with. Black ones are things that we're given. What else can I tell?
The other angle right next to the right triangle is 30.
This one? This one?
Yeah.
Is that what you were going to say? That's got to be 30 because that's a right angle. 60 of the 90 has been used up there. There's 30 left for that one. Okay. There's lots of people that are raising their hands behind you that you can't see. So let me call on one of them. Okay. All right. What else can we tell? Andrew?
Wouldn't you be able to say that the other one is 30?
The other one here?
No.
Here?
Yep.
Okay. Yes, we can because this is isosceles because of the markings, right? Which means its base angles are equal, right? And so what is Y? 120. Because if these two are 30, that's used up 60 of the 180 for this triangle, and 60 from 180 is 120. Does that make sense to you? Now, one more thing that's going to show up that a lot of people can't figure out until they see it, and then they go, duh, of course. If I have an isosceles triangle like this, and the sides are marked or the angles are marked, I don't care which one, and I tell you that this angle up here is 58, then what are these? $61. Because here's the deal. In every triangle, I don't care what it is, there's 180 degrees to go around. We've used up 58 of those, right? Whatever remains has to be split evenly between these two because they are equal. So the process is this: 180 minus the 58, that's 122, And then you cut that in half. Cut the 12 in half, you get a 6. Cut the 2 in half, you get a 1. These are each 61. So if you know the vertex angle, you should be able to find the base angles. They have to split the leftovers evenly. Follow? Okay. Here's the assignment. On section 5.4, these are the ones I want you to do. Numbers 1 through 7, 9 through 11, 13 to 16, 21. And I'm looking through here and I don't see, so, that kind of thing. There we go.